Check, check. Okay, students at home, you can hear me, see me, everything good?
Yes, sir.
Okay. You can see my shared screen? All right. Okay, I think we're ready to go. How are y'all doing? Yeah. Okay, so for next class, we're going to be covering 6.3. We're going to start 6.3 today, but we're just going to get through the first part of it, which is like a preliminary setup to get us really deep into 6.3. So 6.3 is going to require that you remember partial fraction decomposition. That was something that you did either in the beginning of pre-cal, maybe in college algebra. So I sent an email out probably what 10 minutes ago, 15 minutes ago, that has a link to 2 lecture videos that I did in pre-cal class over that topic. And then the homework solution video for that section from pre-cal. If you want, you can watch those if you don't remember how to do partial fraction decomposition. I will say that the problems that we do in here are going to be a little harder than the ones that you did in pre-cal. So just heads up, warning on that. The other thing is bring your graphing calculators. So how many of you do not have a Texas Instruments graphing calculator? Do you have a graphing calculator or you just don't have a graphing calculator? You don't own one at all?
Hey, Professor, I have a question about that.
Okay, hold on at home. You have an app on your phone. Okay, I don't know if it'll do what we need to do. And during a test, you can't use your phone. So I'm not saying you need to go out and purchase one. The tutoring labs, I think, will loan you one if you have a student ID. I don't know if they'll let you check it out for like you leave with it and come back, but you might want to look into that. What's your major? Yeah, so it might be time to invest in one. You don't need anything fancy. TI 84 plus is good enough for most of what you need. Okay, question at home?
No, you just answered it.
I did? Okay. All right, so make sure you bring those because I'm going to show you specific keystrokes to do basically partial fraction decomposition for us. Like we'll be able, well, no, it won't do that. It'll solve a system of equations for us. So it'll save us a lot of time on a test if we can have the computer or the calculator solve the system. Okay, so that's for next time. What else? Let me see, this looks pretty dim. Let me try to brighten this a little bit. There we go. Okay, so we are going to now get into the material for today, which is actually, we're going to continue 6.2. And I want us to do, we're going to do 2 problems, 2 integrals that pertain to the ideas from last class. And the reason I'm doing these 2 specific ones is because something happens within the work that we haven't seen yet. And I just want to make sure you see it at least once. Okay, so here we go. We've got the integral of the square root of x squared minus 25 all divided by x dx. Now on the side, I included here a little chart. This chart comes off of your formula sheets, which I actually finally downloaded. So here's the formula sheet that you're allowed to have on your exam. Remember, you have to print those out. You have to have a hard copy of those for the exam, right? Okay. And there at the bottom, you have this table. So this is all you're going to have on the exam. So we need to get used to the idea of using this, right? So let's go to our notes here. And why does everything look so small on my screen? It's really weird. Okay, there we go. So we are going to be doing this. We see square root. We've got a variable squared minus, well, 25 is a number squared, right? So this looks like x squared minus a squared under a root. When we see x squared minus a squared under a root, we are thinking that make the trig substitution that x is equal to a secant theta, right? So that's what I'm going to do here. What's a for us? 5. Okay, so here we go. I'm going to make our trig sub. X will be replaced with 5 secant theta. And then we take the derivative of that, which would be dx is 5 secant theta tangent theta d theta, right? That's the derivative of secant, 5 secant theta. And then here's the part that's not on your formula sheet that you're going to have to either remember or derive it yourself. And that is, what does the square root of x squared minus 25 turn into? That turns into something. What is it? See, the formula sheet doesn't tell you, does it? Doesn't tell you. Tangent. Okay, so how could we convince ourselves of that? The way that I guess, without actually plugging things in, the way I think about it is, I guess I have to mentally plug it in. Like if I replace this x right here with 5 secant theta, if I square that, right, under the square root, if I square it, it becomes 25 secant squared theta, right? And then we still have minus 25. Yes? So you've got a secant squared theta, 25 secant squared theta minus 25. And then I go up here and I say, where in here do I have something like that? Well, here's secant squared theta minus 1. That turns into tangent squared theta, right? So we have 25 secant squared theta minus 25. So this should turn into 25 tangent squared theta, right? But then we have to take the square root of it, which should turn it into just 5 tan theta. So you either need to like plug it in for x and work it all out like I did in class, or you just get to the point where you can do it a little faster. Does that make sense, or do I need to explain that more?
Can you do it once?
I'll do it once. Okay, so if you replace this x with, what are we replacing x with? 5 secant theta, right? So if I take 5 secant theta and I square it and then subtract 25, this will be the square root of 25 secant squared theta minus 25. Both of those have a 25 in them, so I can factor out a 25, which leaves me with secant squared theta minus 1. That makes sense? Now, what is secant squared theta minus 1? Well, there you can use the chart. That's tangent squared theta, right? So I can replace that in parentheses with tangent squared theta. And now I take the square root of both of these, which would leave me with 5 tan theta. That makes sense? Sure?
Yeah, I think I need to practice it like 3 or 4 times.
Okay.
And then I'll do it.
Yeah, you want to get to the point where you've done it so many times, you kind of know what each one of these turns into. But if during the test you blank out, just plug in and simplify. Okay, so this square root of x squared minus 25, that turns into 5 tan theta. And at that point, we're ready to rewrite everything. So I'm gonna take this right here. I'm just gonna move it to the side so that we don't get it confused with other stuff we're doing. All right, now we rewrite the integral, right? So I'm going to replace the whole square root there, right? That gets replaced with 5 tan theta. The dx, don't forget the dx, gets replaced with everything there. And in the denominator, I happen to have an x, right? And we know x is 5 secant theta. So I'm just going to replace everything now. And now I'm going to have a new integral, and this will be a trig integral. So the numerator is 5 tan theta. The denominator is x, which is 5 secant theta. And then the dx was 5 secant theta tangent theta d theta. Yes? So 5s cancel, secants cancel. So what are we left with here? 5 tan squared theta. D theta. And I can pull the 5 out, right? All right, so now we're faced with, I'll go ahead and pull the 5 out. Let's get that out there. Equals. Okay, so how do we handle tangent squared. There's a couple of different ways we can do this. So anyone have any ideas?
The reduction formula?
Which reduction formula are you referring to?
It was the,
Do we have one for tan squared?
no.
I don't
Right.
think we have, on our formula sheets, we don't have anything to handle tan squared. There's nothing on here for tan squared.
Also, would it be like a Pythagorean identity?
We can use a Pythagorean identity.
The sine squared over cosine squared.
We could turn it into sine and cosine also. So it's kind of like there's different paths we can go down here. If you want, you can look at that as sine squared over cosine squared. You can do that. I also heard Pythagorean identity. We can change tangent squared into what?
Isn't it 1 minus cosine?
Go to this right here. Yeah. We can change tangent squared theta, right, into secant squared theta minus 1, can't we? Well, the only thing that would be useful there if we did that is if we could then integrate those. Let me write it down. That becomes, if I wanted to, secant squared theta minus 1. Agreed? Now that's only useful if you can actually find the antiderivative of each of these, which you can, because the antiderivative of secant squared is something you know from Cal 1, right? 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 Because the derivative of tangent is secant squared. So the antiderivative of secant squared would go back to tangent, wouldn't it? And then the antiderivative of 1 would be theta. Right? So that Pythagorean actually makes this problem work out pretty simple. I mean, relatively easy. With relative ease. I said this on the homework video too. Okay, so we can do this. Now look, I'm not going to go down. We could have done sine cosine and tried to see and mess with it. There's a, maybe there's 4 or 5 other roads you could have gone down. This one I think is the cleanest way. I'm taking the antiderivative. So the antiderivative of secant squared theta is tangent theta. The antiderivative of 1 is theta because our variable is theta. And then we just say plus c. All right. We're not done, right? We got to get everything back to x now. So to get things back to x, I always say go back to your original trigonometric substitution, write it down. It was x was it 5 secant theta? Yeah. And then I say create the ratio out of that. So get rid of that 5. And then from that, secant theta is x over 5. We draw a reference triangle. And theta is the angle here. Secant is the reciprocal of cosine, right? Cosine is adjacent over hypotenuse. So secant should be the hypotenuse over the adjacent. So that means I can label the hypotenuse x and the adjacent 5. So I was thinking about this. I remember being in Cal 2, and I remember this side of the triangle that my professor would not show where this side came from. And I remember being there going like, where's that coming from? I know that may seem stupid to you, but I'm going to just do it just to make sure you understand. All right. This side comes from, we don't know what this is, right? So I'm just going to call it, I don't know, B. And then I use Pythagorean identity with the right triangle that a squared plus b squared must be equal to c squared. So 5 squared plus b squared must equal x squared. So the 2 shorter sides squared added together must equal the hypotenuse squared. And I want to solve for b. So I square the 5. I move the 25 to the other side. And then the last step would be to take the square root on both sides. And I will only look at the positive root because it represents the length of a side of a triangle, so I don't want to have a negative there. So this side right here is the square root of x squared minus 25. Normally I don't show that step, but that's because in pre-cal, if you have 2 sides of a right triangle, you should always be able to solve for the third side doing that. But I didn't show that last time, and so I just wanted to, I guess, go back and try and remember what it's like to be a student. Sometimes you need to see those little things. So, okay, we good? Yes.
Can I ask a freak out question?
You can.
What's the, how do you know which one's opposite and which one's adjacent?
Opposite, so you have to label the angle first, right? So here's our angle. I could have labeled that angle on the bottom or the top right corner. It's up to me. I'm just drawing a triangle. So I'm saying, hey, let's call this theta. The angle that's opposite of that would be if you were just looking from this corner out to the opposite side, right? So the side opposite of the angle. And then adjacent would be the one right next to it, which would be
Yeah,
this one. The hypotenuse is always the longest side.
and how do you know theta goes there?
I could have done theta anywhere I wanted. I could have done like this if I wanted to. If I call this theta, now this is the opposite side, and that's the adjacent side, and this is the hypotenuse, and everything would still work the same way as long as you label everything correctly. So if I use this triangle, then the hypotenuse here would be x, and the adjacent would be 5. You see, x, 5, and then this side would be your square root of x squared minus 25.
Yes, sir. Thank you.
Okay. So it's an arbitrary triangle that we're drawing. The only thing we need is that triangle must match the equation. So it must maintain the relationship we have here with the secant theta being x over 5. Okay, so we've taken the antiderivative, we've drawn a reference triangle. If we want to know now what tangent of theta is, right, then we need the opposite over the adjacent, right? Opposite over adjacent off of this triangle. So this will become 5, and then opposite is the square root of x squared minus 25 over the adjacent, which is 5. Everyone good with that? Okay, here's the difference. Here's the part of the problem that's different than what we did before. We need to figure out what theta is, right? Theta. I can tell you what tangent of theta is. I can tell you what sine of theta is, cosine. I can do that because I have the triangle, right? But to say what theta is something different. We haven't been asked that before. So it's actually pretty easy. What we're going to do, let me get rid of this. What we're going to do is we're going to go back up again to where we have our relationship here. No, sorry, second one right here. This one, which we drew the triangle on, and we're going to solve it for theta. So all we're going to do is kill off the secant on the right-hand side by bringing in the inverse secant on both sides. So I bring in inverse secant on the left side, or arc secant on the right side. And the cancellation property says that when you put together a function and its inverse, they kill each other off. So that leaves you with theta on the right side. And the left side, well, it's secant inverse of x over 5. And that's what theta is. All right. So I'm just going to stick that in there for theta. Minus secant inverse of x over 5. All of that plus c, we're done. So we had not, that was the part we had not seen, is how do you solve for theta? We actually don't need the reference triangle for theta. We only need the reference triangle if we see like tangent or cosine or sine or something like that, which most of the problems you do. But this problem, we had a theta. Does that make sense? Any questions?
What about the 5? Are you going to,
We could distribute it. Is that what you're saying? The 5 on the very outside?
yes,
Yeah, we could, if we distributed through, it would cancel here, right? And it would be a 5 out in front, and that would be it. Obviously, the
would we
5
need
could
to
not,
on the test or no?
you wouldn't need to, no. Yeah, that's kind of a, not a necessary step. Now, we could differentiate this, right, and check it. I'm not going to, but if we did, we would have to know what the derivative of secant inverse is, wouldn't we? And that you would have to go to your formula sheet and look it up, because that's not something most students know right offhand. So here are the derivatives of the inverse trig functions. Here's a derivative of secant inverse right here. So you could use that to go check your answer. All right, any questions before we do the next one? All right, so this problem, one difference you'll see right away is I'm using a different variable. And that's just because we don't always have to use x, right? We can use different variables. So we have the integral of 1 over t cubed times the square root of 4t squared minus 9 dt. It's enough. I know I've said it. I said it last time, and I've said it throughout this class, is that, you know, you don't want to get yourself with tunnel vision where all you're doing is saying, oh, this is obviously trig sub. I mean, you have to consider the fact that maybe it's a basic U sub. Maybe it's an integration by parts. Like, you know, there's like a big asterisk in front of everything we're doing here. And that is, you've thought through the other possibilities first, and now you've concluded you're going to go with trig sub, which we are. We're going to do trig sub here. Now, which one of these forms does this look like? Do we have this top one here, middle one, bottom one? It looks like the bottom again with one issue. What's the issue? The 4, right? We cannot have the 4 here. So what we're going to do is kind of what we did last time. We did one problem like this. I'm going to just work with this algebraically. 4t squared minus 9. I need that 4 to be gone. So I'm going to factor a 4 from both of those terms, which leaves me a t squared minus 9/4. I did that in my algebra class yesterday. Did something like this where I factored and they didn't like this. They didn't like that at all. But we all understand you can do this, right? Okay, and now this splits up, right? You can actually pull this 4 out as a 2. And so if I pull that 4 out as a 2, then that 2 would sit in front of this root, and that 2 would be next to this t cubed. I could pull it in front of the t cubed, and I could pull it out of the integral as a 1/2 out front. So I'm going to do that. So I've got a 1/2 out front, integral 1 over, okay, t cubed square root of t squared minus 9 over 4 dt. All right, now we can use the formula, right? Now we can. What would A be? What would A be? It's this number, right? The square root of it, right? So the square root of 9/4, take the square root of the top and bottom, 3 over 2. Okay, so A is 3/2. I'm just going to kind of note that here. That's A squared, which means that A has to be the square root of that, which is 3/2. So just to be clear. So what is the trig sub that we're about to do here? Secant again, right? A secant theta. So the trig sub, let me go ahead and just write it down here. The trig sub I'm doing is that x, no, not x. What is it? T, right? Because we won't have x in the problem. T must be equal to A, which is 3/2 secant theta. Okay, and then I'll take the derivative of that. So dt will be 3/2 secant theta tangent theta d theta. And the square root of the t squared minus 9/4 will be equal to, so here's that step that we were talking about earlier. Like, do you know what that becomes, or are you going to have to work it out? Well, going off of what we did last time, we know this can turn into A tan theta, right? A tan theta, so that's going to be 3/2 tan theta. There we go. Now we're ready to plug everything in. Any questions before I proceed? Let's just highlight what's going to be replaced. That t right there is going to be replaced with this 3/2 secant theta. Just the t, I still have to cube it, right? You'll see that? And then the entire square root, the entire thing, is going to be replaced with 3/2 tan theta. And don't forget the dt, right? That'll kill you. That dt has to be replaced with all of this. So here we are. We have this equals 1/2. Okay, integral. Oh, we have a 1 on top. That's nice. 1 over. Okay, t cubed. So I need to take this yellow thing and cube it. Now I'm actually not going to cube the 3 halves. I'm just going to put 3 halves and put a cubed on it because I might get some things to cancel. So I'm going to go 3 halves cubed and then secant, I'm going to cube that theta. So that's the yellow part cubed. Y'all agree? Next to it on the bottom, I have the blue part, which is another 3 halves tangent theta. Okay. And then I have to multiply all that by dt, which is out here to the outside. And that's the green part, 3 halves secant theta, tangent theta, d theta. And now I try and see if I can get some things to cancel. I think I do actually get some pretty good cancellation here. That 3 halves cancels. The tangent cancels, right? And one of the secants cancel. The one here, and then this 3 will become a 2. We good? Let's go ahead, since this 3 halves cube, let's go ahead and cube it. What would this be if we cubed it? 27 over 8, right? We cube the top cube, 27 over 8 on the bottom. So if you have 27 over 8 on the bottom, doesn't that turn into 8 over 27 on the top? So I can flip it back up and then pull that out. I'm just going to write it. We'll clean it up on the next step. I'm going to have the 1/2, and then the 27 over 8 that we had on the bottom gets flipped up as an 8 over 27. I pulled it out of the integral. I will clean that up on the next step. That, you know, I can reduce that out, but I just want to make sure everyone understands where the 8 over 27 comes from. Good? Okay, what's still in the integral? 1 over what? Secant squared theta, d theta. All right, I'll go ahead and clean that up on the outside. Let's see, that 2 goes in there once, that's 4. So we have 4 over 27 integral. Okay, 1 over secant squared theta d theta. How are you going to handle that? Careful, the antiderivative of that is not tangent theta, right? Because that's not secant squared. That's 1 over secant squared, right? What were you going to say? Yeah, let's just switch that over to cosine squared theta, right? Just 1 over secant is cosine, so let's just change it back to cosine squared. That's what it is, right? And now, how do you handle the antiderivative of cosine squared? That's right, that power reducing formula. So this is when you have cosine to an even power or sine to an even power. This is earlier in this section. We're going to use a formula. I'll remind you of the formula right here. Cosine squared theta equals 1/2 times 1 plus cosine 2 theta. That was the power reducing formula, right? Or the halving, what do they call it? They call it the half angle formula. I call it the power reducing formula. So I'm going to just use that and rewrite this in here. So now we have a new integral. It's 4 over 27 integral, the 1/2 here. And then I have 1 plus cosine 2 theta d theta. I should have pulled that 1/2 out. Maybe I will. I'll pull it out now. And when I pull the half out, it's going to reduce with the 4. It'll become a 2 over 27 integral 1 plus cosine 2 theta d theta. Y'all good? Y'all feeling good? Having fun? All right, can you find the antiderivative of each of those? Yeah, we should be okay with those, right? Antiderivative of 1 theta. Careful. Antiderivative of cosine 2 theta. Close. Let me write down what you said. You said minus 1/2. What's that? It's plus. Okay, good. Plus 1/2. That, you see, it gets confusing. Like, which direction are you going? Okay, so 1/2 sine 2 theta and then plus c. We good? All right. So now we need to get theta back to x, right? Theta back to x. And to do that, I have to use a reference triangle. Well, hold on. This theta is like the last problem, isn't it? See, that doesn't have a trig function with it. So I'm going to probably have to do like an inverse thing like we did before. But this is the new thing on this problem. This is new. We haven't seen this before. We've seen things where our answers like sine of theta or cosine theta or secant theta or tangent theta, but we've never had 2 theta. And that creates a problem. Because when we go back to what our sub was, what was it? T. Did I say go back to x? I should have said go back to t. Our sub was 3/2 secant theta. That was our sub, right? Okay. If we're going to try and get from theta back to t, not x, then we can use this to draw a triangle. Okay, so I multiply both sides by 2, I divide both sides by 3, and I now have a relationship to draw my triangle. But what is the angle in this triangle? What's the angle? Well, I have to go off of this information, right? It's just theta, right? So this is theta. And then secant is the reciprocal of cosine. So that means the hypotenuse should be 2t and the adjacent should be 3, right? Just going off of this, that's the drawing for it, right? And solving for the other side without showing the work, this would be 4t squared minus 9. Okay, so that part there in green, I'm not showing that work, but I did it earlier today, so hopefully that helped. But again, the key here is that this triangle gives us all the information we need about theta, sine theta, cosine theta, tangent theta. But our integral, our answer, has 2 theta in it. So this is apples and oranges. We can't use the information off the triangle unless we realize we can do what with this. We can rewrite it, right? With the pre-cal formula. A double angle formula from pre-cal, a very important double angle formula from pre-cal that I hope you remember. Maybe you'll remember it when I write it down. Sine 2 theta equals 2 sine theta cosine theta. That is a double angle formula from pre-cal. It's on your formula sheets, and it's a big one. It comes up a lot. So if I use that formula and I replace this blue part with 2 sine theta cosine theta, then I get some nice stuff here. This becomes 2/27 theta plus 1/2 times 2 sine theta cosine theta, and then plus c, cancel. So now, in order for me to find the answer, I just need to know what sine of theta is and what cosine of theta is, and that I have the triangle for that. Okay. And I need to know what theta is. How am I going to get theta? I'm going to take arc secant on both sides of this to get theta. So let me write down, I'm going to write down the answer. And hopefully you can tell me whether or not you understand where all these pieces come from. Theta becomes arc secant of 2t/3. And then plus, now sine of theta, I go to my triangle. Sine is opposite over hypotenuse. So square root of 4t squared minus 9 over 2t times cosine theta, which is adjacent over hypotenuse, all of that plus c. And I guess I could put these two together. Maybe I'll do it one more line. I'm not even going to distribute the 2/27 through. I'm just going to leave it out here. Plus 3 root 4t squared minus 9 over 4t squared. plus C. There we go. Yeah. So all the problems that we did last class, when we got our antiderivative, we did our reference triangle, and the reference triangle was all we needed, and we were able to do it. Today, these two problems demonstrate that sometimes you need to know what theta is. So you're going to need to do like an inverse on, an inverse trig up here on this piece, do inverse. So if that said 2t over 3 equals cosine theta, then we would have done our cosine on both sides, right? So sometimes you need that. And then sometimes you might need a double angle formula because, we've seen like, where did the double angle come in here? The double angle came in when we were trying to take care of cosine squared, right? What if we have an integral where we have sine squared? We're going to see it again, right? So it is possible that we may need double angle formulas in here. All right, questions? No? All right. Where did that go? Hold on a second. Where did it go? I have a window that's disappeared. Where is it? There it is. Wow. Really strange. All right. I want to point out one more type of issue that you could run. We're not going to do the problem, but I know that there's a problem like this in the homework where you have something like, I don't know, I'm just making this up, something, and then on the bottom you have like x squared, let's say minus 4 to the 3/2 dx. So this doesn't immediately look like trig sub because with trig sub, you're looking for that square root, right? You're looking for it. Here, you just have to realize that this is actually the same as the square root of x squared minus 4, all of that cubed dx. Pardon? Yeah, you can do u sub on this one. I'm just, yeah, let me change it to a cubed on top. That'll make it a little harder. Well, I'll make it to the 4th. That way you're not tempted to do anything else with it. Okay, so here we'll do a trig sub. We have to rewrite the bottom this way, the square root cubed, and then do your trig sub here. And then just don't forget you have to cube it once you replace that. Okay, so just be careful. Yes.
Can you also separate two, like do the square root of 1 times the whole of the other?
Wait, say again.
Can you like separate two, like I do the square root of 1 and then times the whole itself? Does that make sense?
The square root of
Like,
1.
Like in the exponent is like 1/2 times 1. You say, I think you're saying take one square root out and then keep one.
I'm not. Oh, yeah. I know what you're saying. Yes, I know what you're saying. Do this times this.
Yeah.
That's what you mean. Oh, okay. Yes, you could. Yes, you could. And then this would be your trig sub right here. And so like what would the trig sub be for this? That's variable squared minus number. So this would be a secant theta again, wouldn't it? So 2 secant theta. I don't want to work through this whole thing. 2 secant theta tangent theta. D theta would be your derivative, and the square root thing would be 2 tan theta, right? That would be what we do here. So this piece would become 2 tan theta, right? I'm just curious how you would deal with this piece. So you could just replace the x with this, right? Or you could realize that this is the square root of something squared. Like this is that same expression squared. So you could just do 2 tan theta right in here squared. You see what I'm saying? And so I think this way kind of kills all of that with one swoop. Does that make sense? You don't have 2 different expressions. You have one thing to replace and then cube it. I think it's just cleaner, but you could do it that way. Okay, all right. So we are officially putting this section to sleep in terms of what we're doing in class. You obviously need to go do all the homework and practice, right? But now the next section, all right? 6.3, and this is we've come to the end. This is the last section for learning techniques to do antiderivatives. So after this, there's no other like new method or anything else, all right? This is it. And if from here on out, if we get an integral that we can't do by hand, then we just can't do it by hand. All right. All right. So here we go. Partial fractions, preliminary stuff. All right. So some things that we need to understand right off the bat. We all need to be familiar with this formula right here. So I'm gonna copy this formula and I want to talk about it. We've seen it in a certain form. This is a more general form of the formula. So we've seen a formula that looks like this. Integral 1 over, well, let's look at it because on our formula sheet, I don't remember how it appeared here. Let's see, 1 plus, okay. So I did 1 plus. So this right here, we've known for a while because I told you put stars next to it, that this is arctangent of x plus c, right? So that right there, we should have known this already today, right? That look familiar to you? Yeah. This formula is a generalization of this idea. And so what we're doing is instead of using the variable x, we're using the variable u. So we have u squared. And instead of 1, it can be any number squared. So if this was 1 over 4 plus x squared, we have a way of getting the antiderivative. Okay? It only works though if this is a plus in between. So as an example below this, let's just make sure we know how to use a formula. If I have integral 1 over, let's say, x squared plus 9 dx, we should be able to say, oh, that's just this formula, right? U is x, a is 3, right? So this should just be 1/3 inverse tangent of x over 3 plus c. Done, move on, nothing else to worry about, all right? Happy? Do another one. 1 over x squared plus 5 dx. Can we use the formula? We can still use it, right? But see, 5 is not a perfect square. That's okay. It's still a number, isn't it? So in this case, a would be what? The square root of 5, right? So I'm going to put 1 over root 5 inverse tangent of x over root 5 plus c and box it up. It is okay to leave the root 5 down here. You do not have to rationalize this. Okay? What if it was a minus? Just out of curiosity here, what if it was 1 over x squared minus 9 dx? Can you use this formula? You could pull the negative out on the bottom, right? So let me see. If I did that, it would turn into this. Negative out here, that gives me negative x squared plus 9. Negative 1, I can pull that out front, yeah. Just a negative 1. But does this match that formula? Still doesn't. See, in this formula, both of these things have to be positive for this formula to work. So this, right, yes, we could do this algebraically, but it doesn't fix anything. So the question is, what do we do, right? Well, we don't use that formula, all right? And this is an open question. We will return to this, all right? We will return to this. There is actually a tricky way you can do it. We're not going to do it this way because it's too much work, but you could do this. It's kind of insane, but you can do it. You can rewrite the bottom as the square root of x squared minus 9 squared dx. I mean, isn't that the same thing? If I take the square root of x squared minus 9 and square it, that's this, right? And then I could do trig sub. But let's not go down that road. There's an easier way to do it. And it's going to involve partial fractions, but we're just not there yet, okay? For now, if we see 1 over our variable squared plus some number squared, we should be able to do this problem, or do it using this formula, all right? So let me give you one. I'm going to give you something to work. 1 over x squared minus 4x plus 7 dx. Now I'm telling you that this is formula 17, the one I just gave you. But it doesn't look like it, does it? What's wrong? What's making this not look like the formula 17? What's out of place here? What's different?
The
The
minus
x
4.
squared is a variable squared, right? The 7 is like a number squared. It's that minus 4x in the middle that kind of throws everything off, right? If that minus 4x wasn't there, could we use the formula? Yeah, right? If the minus 4x wasn't there. So we did something last class. What do? We completed the square. So I'm going to complete the square on this. So how do we complete the square? Make sure there's a 1 out front, right? Which there is. Okay, so I take the number in front of the x, which is -4, divide it by 2, which gives me -2. I add that, or sorry, I square that, right, which is 4. I add and subtract that. Now, saying that, sir, you all right? You know, both, okay. You sure? Okay. Got this look of, so I'm taking that number, dividing by 2, that gives me -2, then I take that number and I square it. That's what I do every single time I complete the square. Now I rewrite this. And here's where I come in with that hidden 0. I'm going to take that number 4, I'm going to add it and subtract it. And then I still had that plus 7 out there. The first three terms, guaranteed to factor as a perfect square trinomial, which means it'll turn into something squared. What is it? X minus 2 squared. Now, what do you still have there on the outside, though? -4 plus 7, so plus 3, right? Plus 3. You good? Okay, now this turns into integral 1 over, in parentheses, x minus 2 squared plus 3 dx. Questions? That looks better, doesn't it? It almost, like if you squint your eyes just enough, right? Squint your eyes, you kind of have like a variable squared. It's not quite just a variable, it's x minus 2, but it's, you squint your eyes, it kind of looks like something squared plus a squared, doesn't it, on the bottom? Kind of. So to convince us that we can now go to the formula, what I'm going to do is just a quick basic U sub, a basic U sub, not a trig sub, a U sub. So I'm just going to replace Everywhere I see x minus 2, I'm going to replace it with u. What's the derivative of that? Dx, okay? And let's just rewrite the problem. Comes integral 1 over what? X minus 2 is u, so u squared plus 3. And then dx becomes du. Now, does that look like formula 17? Yes. Okay, so this from formula 17 should be equal to, see, a here is what? Root 3, right? Root 3. So using the formula is 1 over a arctangent of u over a plus c. So I'm going to get 1 over root 3 arctangent of u over root 3 plus c. And don't forget one more step. Replace u, right? With what? X minus 2 root 3 plus c. There we go. Yes.
How do you know to divide by 2 on the?
Always, always. You always take the number in front of x and divide it by 2.
Always.
Always. And then take that answer and square it.
Always.
Always.
Okay.
And then add and subtract that number right after the x term. You'll take that number that you got once you squared it. You'll add it and subtract it. If you do that, if you follow that procedure, this first 3 terms will always factor to be something times itself. So something squared. So look, I want to put another problem up here, and I want to see if we can maybe do these a little faster. So let's say we had a problem and we got it down to this point. We had completed the square already, and we got it down to x plus 3 squared plus 9 dx. Let's say, we've been working a problem out and we get to this point right here. Understand? Okay, if we get to this point, do you all see the formula 17 here? Do you see that I could do a u substitution? U is x plus 3, and that du would be dx. So really, I mean, do we have to do all that, or can we just mentally go right to the answer? I want you to get to the point where you can mentally do that. You can see, oh, well, if that's u, the derivative of that's du, and so everything is this is going to switch over to a u, and so I'll have 1 over u squared plus 9. So we just go straight to 1 over a is 3 here, arctangent of the u, which would be x plus 3, right? X plus 3 over 9 plus c. You see? I don't know why I put 9. Sorry, over 3. Thank you. Yeah? See if you really understand that. Say we're working a problem, we get to this integral. That kind of looks like it, doesn't it? I could make a u substitution. What would my u substitution be? 3 minus x, right? What's the derivative of that? Negative dx, which means I would have to scale, wouldn't I? I'd have to like compensate for that negative that would pop out. So that means I'm going to do what the formula tells me, but what am I going to need to put in front of it all? A negative, okay? So this will be negative 1/3, right? Because a is 3 here. Arctangent of 3 minus x over 3 plus c. See, the negative there is coming from the fact that dx was negative, du was negative dx. Du was negative 1 dx. And so we had to scale both sides to get that dx to match up. So let's say we're working a problem, we get something like this, 1 over 5x plus 1 squared plus 4 dx. Again, we kind of squint our eyes. We realize, okay, hey, look, this looks like kind of like a u squared plus 4 on the bottom. So if I let u be 5x plus 1, du would be 5 dx, right? And I don't want a 5, right? So how would I get rid of the 5? Scale it by 1/5, right? Multiply. So I'm going to basically run the formula, but I'm going to put a 1/5 out in front of everything. So it should be 1/5. Okay. That's me scaling out that 5d dx that would happen. And then a is 2, right? So 1/2 arctangent of 5x plus 1 over 2 plus c. So again, this right here comes from the fact that when I did du, I would have got 5 dx, and I need to get rid of the 5, so I scale both sides, multiply both sides by 1/5. Yes?
Would that be a 3 or would it be that 1/2?
I changed this to a 4 instead of a 9.
Oh,
I was just, I just
that's
wanted
right.
to change it up a little bit.
I apologize.
Yeah, no, it's okay. All right. One more, promise, one more. Okay, here we go. So what about this? Integral 1/, what if this was x squared plus 1 squared plus 9? I'll go back to 9 dx. Can we do it here? Seeing a no, why? Why? Yeah, so if we try and imagine that this would be our u, right? The derivative of that would be 2x dx, 2x dx, right? And that we can't scale appropriately. We can only scale it out if we have a number. We can compensate for that being off by a constant. But here we'd be off by more than a constant. We'd be off by. And so you cannot do it this way. So this would not be correct to go to the formula at this point. So in general, let's see if we can generalize this. I think we can. In general, if you're working an integral and you have something over here that's linear, right? It has to be linear. So something like this, ax plus b, right? Plus, I'm going to have to use a different letter over here. I can't use a squared. I'm going to have to use something else because I'm already using a over here. So how about I just c squared? Yeah, little c squared dx. If we saw something like this, right, where the inside here is linear, a linear expression, then my answer will be, well, I have to treat that as a u, right? And when I take its derivative, what's the derivative of this? A dx. So I'll have to scale that a out. So I'll have to have a 1/a out here times, now I can use the formula for arctan. Now be careful because the formula we're using c here instead of a, right? So it'll be 1/c arctangent, careful, arctangent of what? Ax plus b, that's our u, right? The ax plus b over c plus capital C. I'm just generalizing. You don't go and think about memorizing that formula or anything. I'm just showing you how that kind of illustrates the main idea, that as long as we've got something where that in there is linear and squared, and we've got plus a constant squared, we should be able to go directly to that formula as long as we compensate for the number in front of the x. That was kind of like with the cosines. Remember, like when you just did that cosine antiderivative of cosine 2 theta, we had to bring a 1/2 in. It's the same principle of trying to scale out that constant in front of the linear expression. Okay. We move on. So preliminary stuff. Yes.
Is that just a rule, the filling out, like on the third example where you pull that 1/5?
Mm-hmm.
Is that just a rule or?
Mm-hmm. That's what I'm trying to say, is that if you have as long as this looks, right? As long as this thing looks like, that can be our u, right? As long as it looks like 1 over u squared plus a squared, and that thing in here is linear, right? 5x plus 1 is linear, then you can use the formula, but you have to scale out by whatever kills off of 5, so 1/5.
Okay.
And that'll work anytime you have a linear. See, here we did the same thing. What was the number in front of x here? -1. So I put a -1 in front. Here, well, here you didn't have to put anything because what's the number in front of this? 1, right? So you scale by 1, but that doesn't change anything. Yeah. All right. So that's the first preliminary thing. Let me just give you a roadmap of what we need to do here. We have, what, 40 minutes? I'm going to go through, and so what I'm saying here is, here are some integrals that we should be able to handle right now, okay? There's nothing that we need to learn to handle these integrals that I'm about to show you. 1, 2, 3, 4, 5, 6, 7, 8, 8 integrals that we need to make sure we can do right now. And then next class, we will start to do the partial fraction decomposition stuff, okay? So let's look at this first one. Now, just like everything else in this class, these first 7 or 8 problems I'm about to show you that you theoretically should be able to handle right now. If you can't do these, you can't do the next section, the next part of this section, because everything in the next part of the section is going to take us back to this. So everyone look at this. This is an integral where you have a constant on top and a linear expression on the bottom. Constant on top, linear expression on the bottom. That means I can pull the constant out, right? Now, just like we did with the arctan, I want you to think of this like big picture. If you did a u substitution right now, where the bottom is u, right? The whole bottom is u, because that bottom is linear, isn't it? So if the bottom was u, what would du be? 1 dx. So you wouldn't have to scale anything, would you? So that integral, if you just kind of like squint your eyes enough, doesn't it just look like 1 over u? And what's the antiderivative of 1 over u? The natural log, right? So this should just be 2 natural log of the absolute value of x minus 4 plus c. We want to get to a point where we're not making all these little u substitutions. We need to be able to just do these by recognizing what they are. Constant over linear, constant comes out. 1 over a linear is going to be antiderivative is natural log of that linear expression. Look at the next one. Same type of example. Constant over linear again. What's different here? The -5 that's going to pop out, right? If we were to, again, squint our eyes and say, oh, this whole denominator, right, can be like the u, then the derivative of that, right, the derivative of this would be -5 dx. And we wouldn't want that -5 there, would we? We want to get rid of it. So we're going to have to scale by what? -1/5. -1/5. So what would this answer be? Remember, we're really kind of squinting our eyes and saying that this is a u here, right? This du, we actually had to multiply it by -1/5 to make it match. So we get our, oh, and that 2 out here is not a 2 in front of the integral. That's number 2, okay? So just ignore that. So what would this answer be? Who wants to give that to me? -1/5.
The natural log of the absolute value of 4 minus 5x.
1 minus 5x, boom,
Plus
plus c, we're done. Okay. We do not want to be doing that slow, you know, u equals this, du equals that. You'll run out of time on a test if you have to do every little thing. Okay, so constant over linear, I'm hoping you can handle. Let's see what our next example is. Constant over linear. Ooh. Constant over repeated linear. So look at that, look at the denominator on this one. 2x plus 1 is linear, right? But you're squaring it, which means you're repeating that factor over. Could you still treat that, like in your mind, could you still treat that thing down here as a u?
Yes.
What would the derivative of that u be?
2u.
2 dx. So you'd want to get rid of the 2, right? So you'd need to scale by a half. Agreed? Now, there's a little trick here. I mean, it's a little tricky because if you do this, that's not 1 over u, it's 1 over u squared. And the antiderivative of 1 over u squared is not natural log anymore because of the squared. So let me see if I can rewrite this. This dx is really going to become a half du. Again, because of the whole idea of having to kill off that 2 in front of the x. So this integral really looks like this. Right? It's really what, if I made a u substitution, that's what it would look like. The 1/2 killing off the 2. Are there questions? Now that is u to the negative 2. And now you just use your power rule. Good old power rule for antiderivatives, right? So the antiderivative of u to the negative 2 is negative u to the negative 1, right? Because you're adding 1 to the exponent. You have to multiply the front by 1 over negative 1. So this should turn out to be the negative. I'll just pull it out to the front, u to the negative 1 plus c, which is negative 1 over 2. Now that u to the negative 1, I'm going to drop it back down. And what is u? I forgot what was u. We never wrote it down. Just 2x plus 1 plus c. Do you think you understand that? I think I want to give you another example. Let's see if my notes have another example of that. Yeah. What's good about this one? Do y'all see the good news with this one? There's something really good about it. You don't have to scale it because there's a 1 in front of the x. So you don't have to scale anything out because if you treat the x minus 5 as u, the derivative of that's just du is dx. So there's no scaling. So that's great, which means really this integral looks like what in our minds? 1 over u cubed.
Negative 3.
So u to the negative 3 du, no scaling involved. And that should turn out to be negative 1/2 u to the negative 2 plus c. Power rule. And then that would be negative 1 over 2 u squared plus c. U was x minus 5. I hope what you see from this is once you get the rhythm of this, when you see these should be just kind of like trivial mental exercises. Maybe not yet for you, but that's where you want to get to, all right? Shall we keep going? We're ready on number 4. Wow. So everything we've dealt with this up to this point with these examples I've given you here. Okay, everything, well, what have we seen? Let's just recap real quick. Linear over, constant over linear, right? We can handle. Constant over repeated linear. That means you have a constant on top, you have a linear on the bottom. It might be squared, might be cubed, whatever, we can handle that. Here, got something different. A constant on top, a quadratic on the bottom with no x term. X squared plus 9. There's no x term in the middle, right? It's an x squared term and it's a constant. So you've got a quadratic with missing an x term. How are you going to handle that? Formula 17. That's formula 17, right? 1/3 arctan x over 3 plus c. I recap again. Constant over linear, good. Constant over repeated linear, good. Constant over quadratic that's missing an x term, we're good as long as what? If we're missing an x term, we're going to be good as long as what? There is one condition on this. That has to be a plus. If we had a coefficient, like let's say we had, are you saying coefficient on the x? So let's say this was 3x squared. Or let's do 5x squared. I just pull a 5 out. I just pull the 5 out of the bottom, it would become a x squared plus 9/5. And then I could do the formula. So we could handle that. But the key on this is it has to be a plus, because if it's a minus, I showed you earlier, it's a minus, all bets are off. You can't use the formula. All right. Okay, man, we're cranking these, right? It's about to get weird. So what if we have a quadratic on the bottom like this? So what if we have a constant on top? And what if we have an irreducible quadratic? What do I mean by irreducible? Don't know what I
It's
mean?
not factorable.
It's not factorable. Okay, so check that x squared plus 2x plus 17. You cannot factor that. Now, if you can factor it, we will have a way of doing it. And that's what the next class we have is going to be about. All right. So this is how you handle it if it's not factorable on the bottom. Right? That doesn't break into two factors. So if it doesn't, how do we handle this? I actually did this already today. We're going to complete the square. Complete the square. Why don't you do that? Let me give you 5 minutes. See if you can do that problem. Complete the square and then use the formula 17. Now, I'm going to put myself on mute real quick and take a little break. I'll be back. Everyone work this problem. if you happen to finish that problem and feel good about it, you can look at the next one we're going to do. How about at home? You guys have, you have the first one yet?
I have the first one.
Yes, sir.
I'm just going to work the first one. I'm not going to say anything. I'm just going to work it. All right, is that what y'all got for the first one? 1/4 inverse tangent of x plus 1/4. Yeah? Do we have any questions on that? We're good? Okay, the next one is one of my favorite types of integrals out there. Okay, this is one of my favorite. It's not because it's really, really hard. It's because the way you can do this is kind of, it's kind of cool. So I'll start this with this. If you go to a tutor, they're probably going to tell you to complete the square on the bottom. Okay, that's probably what they're going to tell you to do, and then they're going to show you a way of doing it, and it works. And most textbooks do it that way also. I do it a different way, and I do it because I think it's better for your brain. It's just a better mental exercise to do it this way. So if you don't like my way, I'm happy to show you another way. And if you go to a tutor, they can show you something else, but this is the way that I like it. This first thing, this is a linear expression on top. This first time we've had this, right? It's always been constant, constant, constant. If we have a linear expression on top and an irreducible quadratic on the bottom, it's important that it's irreducible. Irreducible means we can't factor it. So we cannot factor that denominator. If we have this, here's the technique that I teach. What you're going to do is you're going to make a basic u substitution of the denominator. The whole denominator is going to be u. Now, the reason I'm doing this is because if the denominator is quadratic, right, and we call that u, the derivative of that should be linear, shouldn't it? If you take a quadratic and you differentiate it, you're going to reduce the power and it's going to go down to a linear. And I know that my numerator is linear, right? So maybe they'll match. Maybe they'll actually match up. Maybe the top will be the derivative of the bottom. Let me see. If I differentiate that, I get 8x minus 4 dx. Agreed? Is that what we have up top? No. Could I, oh, shoot, man. Almost works. Like if these were both 8s, right? What if these were both 8s, right? Then I could just like pull an 8 out or divide by 8 and it would match exactly. It'd be beautiful. It'd be perfect. It doesn't match though. I can't, this is not the top. Do y'all see that? So what I'm going to do, and here's the part, I'm going to make the numerator match this 8x minus 4. I'm going to force it to happen. Okay. So watch how I do this. All right. Just keep in mind, this is what I'm trying to do. I'm going to try and make x minus 1 turn into 8x minus 4. I'm going to try and do it without breaking any rules of math. All right. So the first thing I need is I need the x to become an 8x, right? So to do that, I just need to multiply by 8. But I can't just multiply by 8 just out of nowhere. I have to multiply by 1. So I'm going to multiply by 8 over 8 on the outside of the integral. Okay? So take this integral. I'm going to multiply by 8 on the top and 8 on the bottom. That's not changing the problem, is it? No. But I can leave the 8 in the denominator here, leave it outside, and I can pass the 8 up here through, can't I? And I have to multiply it through both terms. So now my integral looks like this, 1 over 8. And then I have 8x minus 8 on top. And on the bottom, I have 4x squared minus 4x plus 3 dx. Yes? All right, it looks closer now, doesn't it? 8x minus 8. I want it to be 8x minus 4, don't I? What I'm going to do is another nice little trick that we can do in math, and we actually do it when we complete the square. Remember when we complete the square, we add and subtract a number? I'm going to do the same thing right now to make the minus 4 appear. Watch. I'm going to do 8x. Now I want a minus 4 to appear, right? So I'm going to subtract 4, add 4. And then what did I actually still have up there? There was a minus 8 up there, wasn't there? And then all over 4x squared minus 4x plus 3 dx. Is that okay? Any questions? I'm trying to make this 8x minus 8 look like 8x minus 4. So here it is, 8x minus 4. There it is. Yay, I made it. But I have this here now, don't I? Okay, so let me clean this up. This becomes 1/8 integral 8x minus 4 minus 4 over 4x squared minus 4x plus 3 dx. All I did there was put that 4 and negative 8 together. I put those together and made that a minus 4, but I've got the 8x minus 4 right here, don't I? So this 8x minus 4 matches this 8x minus 4, but it doesn't match that, does it? That's okay. Because I'm going to split this now into two fractions. I'm going to make this into 1/8 integral 8x minus 4 over 4x squared minus 4x plus 3 plus -4 over 4x squared minus 4x plus 3 dx. I'm allowed to do that, right? This is just algebra, right? I can split it up. I could actually split it into 3 integrals, couldn't I? Like the 8x over this, -4 over this, -4 over this. But I want the 8x minus 4 together so that this first integral, right? This first one right here, I'm happy about, right? Because that, the bottom is u, right? And the top is du, exactly, perfect, right? I made it perfectly match. So what will the antiderivative of this be? If that's really just u on the bottom and the derivative on the top. That's like 1 over u du, isn't it? So the natural log. Make sense? But now we have this new problem, right? So how do we deal with that? What is it? What's on top? Okay, what's on the bottom? Irreducible quadratic. How do you deal with a constant over an irreducible quadratic? Complete the square. We just did a problem like that, right? I took a break and walked out. Y'all did that type of problem already, didn't you? So now you're gonna have to do it here. Okay. So let me break this into two problems now. It'll be 1/8 integral 8x minus 4 over 4x squared minus 4x plus 3 dx. And then the other integral, be real careful here. The other integral is going to be 1/8. You have to bring that 1/8 with you. -4 over 4x squared minus 4x plus 3 dx. First one, do I need to go through this? Do I need to show the substitution here? Are y'all comfortable with the idea that this is really just like 1 over u du? You're okay with that? So this first integral, my answer will be 1/8 natural log absolute value of 4x squared minus 4x plus 3. Plus, okay, now this one, I'm gonna pull the -4 out. So I'm gonna make it -1/2 integral 1 over. Oh, you know what? I'm gonna have to pull something out there, aren't I? Because if I complete the square on this, I need a 1 in front of the x squared, don't I? Oh, crap. Okay, you know what? I'm just going to write it down right now and let's go work on it. That's going to take a little bit of work. You see what I've done though, right? Started out with a linear over a quadratic that was irreducible. I let u be the denominator. I said, oh, what would the derivative of that be? Oh, too bad I don't have it. Oh, I'm going to force it to happen. Force it to happen, split it into 2 integrals. The first integral is easy. The second integral is going to require work. So here comes the completing of the square. To complete the square on that, I have to first factor a 4 out, which leaves me x squared minus x plus 3/4, right? Now I take the number in front of x, which is a 1, right? Or -1, I should say. -1. I take half of that. So I take half of this number, that's -1/2. Then I square it, -1/2 squared. What's -1/2 squared? 1/4. And that's the number that I'm going to add and subtract. So I'm going to have 4. Then we have x squared minus x. Here comes the adding of that number and the subtracting of that number. But I still had over here a plus 3/4. The first 3 terms are guaranteed to factor. to be x what? Something squared. X. What number goes here? Yeah, you know what? It will always be this number, always. It's always this, not the number squared. It'll always be the number here. The number that you get when you divide by 2, that number will always be the number that goes here. So this will be minus a half. And then the last two come together, and what's negative 1/4 plus 3/4? A half. Plus a half. Yeah, I like it. I like it. I like it. Okay. So this integral, I'm gonna save myself some space here. This integral right here. Well, you know, I can cheat. So I'm just gonna copy and paste. Paste that sucker right here. So this now, this new denominator, right, is what we just got there. It's 4 parenthesis x minus a half quantity squared plus a half. And then that 4, what do you want to do with that 4? Bring it out as an 8 down here on the bottom. So we'll have that 4 is gone, comes out 1/8. And then I don't need the double parenthesis anymore. And do you recognize this? How are you going to do this? Formula 17. Do we have to scale? We have a 1 in front of the x, right? So we don't have to scale. We're there. So this will become minus 1/8. Okay, here's the formula. What is A? A is tricky on this one. What is A on this? Square root of 1/2. So the formula says it's 1 over A. So 1 over the square root of a half arctangent of what?
X minus 1/2
Over
of the square root of 1/2.
square root of 1/2. Let's see. We're done. There's probably some algebra we could do here, but this would be fine on a test if you just left it like that. What do you think? That's kind of weird, huh? Now, would you like to see it the other way? I don't mind showing it the other way, that a tutor would probably show it or the book shows it. Yeah, let's do it. I mean, you might prefer the other way. I'll explain why I like this way more after we do it the other way. All right. Okay, so let's take this problem again. This will probably be the last thing we do today. Okay, so the way that the book does it and stuff, what they would do is they'd first pull the 4 out of the bottom. Okay, so they would complete the square on the bottom, and they would get this x minus a half squared plus a half, right? That's what they would do. Okay, so you still have to complete the square. The rest, though, they just make a u substitution. They go, okay, u is equal to x minus a half. Okay, they're making that substitution right there. Du is what? Dx. Okay, and so now the only thing I need to worry about here, this right here, that's going to be u, right? The only thing I really need to worry about is what does x become? So how can you figure out what x is? Right, because dx is dx, right? Just solve that first equation for x, right? So if you solve that for x, you get u plus a half equals x, yeah? U plus a half equals x. So let me rewrite the problem. This is 1/4 integral. This x becomes u plus a half minus 1, right? That's u plus a half, take away 1, over what? u squared, right? U squared, that's u squared plus a half du, right? Go with me? This becomes 1/4 integral u minus a half over u squared plus a half. All I did there was put the 1/2 minus 1 together, right? Yeah? Okay. Next step, they split it into two integrals. U over u squared plus a half du. And then, so they're splitting it here, right? They're going to do this over this with the 1/4 in front. Then this one, I'll do a plus 1/4 integral negative 1/2 over u squared plus a half du. Do y'all see what I've done there? Do y'all see how we can do the first one? What? Well, that's not a formula because we have a u on top. This one will be a formula. Let me bring that 1/2 out. If I bring that 1/2, it becomes negative 1/8, right? And a 1 on top. The second one, do y'all see that's formula 17? Okay, that's formula 17. This one is not formula 17. Just a basic u sub, right? Just a real basic u sub. Let the denominator be u. Well, we can't use u. We're already using u, right? So we just say, hey, look, notice if we let the denominator be our substitution, the derivative of the bottom is up here, but we're off by a constant. You see that? So for this one, I'll do this one right now. I'm going to do a v substitution. I'm just going to make up another letter. We'll do a w substitution. I'm going to let w be equal to u squared plus a half. And then dw would be equal to 2u du. And we have up top u du, don't we? So we're off by 2. So we scale it, 1/2 dw equals u du. And so how can we rewrite this whole integral? 1/4. Yeah, the u du is going to bring us a half out front, right? The u du is dw. 1 over, what's the bottom? W. So 1 over w dw is this one, which really turns out to be 1/8 natural log of w, doesn't it? The antiderivative. And then over on this one, let's bring this one down. This was minus 1/8. Okay, and then now you need that formula 17 here. And a is 1 over or square root of 1/2. So I'm going to put 1 over square root of 1/2 arctangent of u over the square root of 1/2 plus c. And then you replace u with what? U was x minus a half. And you replace w with what? U squared plus a half. And then you replace that u with x. Yeah, so you get the same answer. Okay. I don't know, which one do y'all like more? You like this one more? Okay. Yeah. Yeah, they both work. Okay. Now, here, the reason why I prefer the other way is because as you move on and do more math, this whole idea of manipulating an expression into something that you want it to be, where you come in with a 1 or you come in with like a hidden 0, is a more advanced kind of thinking thing. This is a little more methodical, where you can just be like, follow the process, I will get to the end. It's less like creative thinking, in my opinion. So that's why I like to show the other way. But I've shown you both. You do what you want. I don't care. You're not going to hurt my feelings, okay? But you want to do this when you have a linear over an irreducible quadratic. Okay. We're out of time. We are going to come back on what, Monday, right? We're ready, time for the weekend, right? So come back on Monday. You're gonna have review partial fractions, and you're gonna bring your calculators, and we're gonna have fun with the rest of this. When's our next test? Oh, we still got a ways to go, huh? Next test is gonna be tough. All right, there's gonna be a lot of material on this next test, because we still have to do 2 more ideas after this. And that'll be what's on the test. So do your homework. Have a great weekend.
Wait, so Professor,
Yes.
on the question we just did right now, you know how you took out the 1/4 outside the integral?
Hold on, let me see. How on the what?
Right here, you know how you took out the 1/4, and then you're left with like that x squared minus 4x plus 3. Isn't that like reducible?
Wait a minute, what?
At the very beginning, you know how you take out the 1/4?
Well, I took out, so I factored a 4 from each of these, right?
Oh, you factored out a 4.
Which we had done on the previous, where did we do it? It was over here, right? Yeah. I completed the square. So in the previous problem, when we did it the other way, I had factored a 4 out and then completed the square, right?
Mhm.
I didn't want to have to show that step again.
Oh, okay, gotcha.
So I pulled the 4 out of this and completed the square.
Okay, yeah, that makes sense.
So it was this right here. Basically, I was just jumped right to that instead of showing all that work.
Okay, that makes more sense now.
Okay,
Alrighty,
is
thanks.
that all you got?
Yeah,
Okay, cool. I got your text. Sorry, I didn't reply. I was driving.
I know you're okay.
Okay,
Thanks.
all right. Have a good one. Yes, sir.